All right, ready to get started? So, to continue our discussion tonight of sampling, we talked last week about how you all at this point now understand how you can take a relatively small sample and with shocking precision estimate the true population mean. I think the question we finished off with was one about the average amount of time teenagers spend online. Millions of teenagers. And we were able to take a sample of, I think, 1,000, which is actually higher than we really needed, but 1,000 gave us a very precise confidence interval. We could measure within, I think, a quarter of an hour how much time these millions of teenagers spend online just based on our sample. So we'll review the sampling distribution of the sample mean, and then tonight we'll just add a little bit to that same concept. We'll learn a couple terms which are pretty easy, and then we'll learn a extension of the sampling distribution of the sample mean, which is just kind of what we do in the real world when we don't have as much information. And that will learn how to read a little table, and we'll learn how to approach things slightly differently, but it's all the same sampling type of concept. And there'll be plenty of time to do a couple of practice problems and make sure you're feeling good about all this material. So, we are talking about estimating a population mean, the average income, the average time spent online, the average whatever. We can't ask every single person in the population, so we sample. It turns out that what we know about the normal distribution helps us with sampling. How things are normally distributed, 68.3 and 1 standard deviation, etc., etc. When we take a sample, if we can assume that sample would fall on a normal distribution, then we can assume all of those things. And that will help us with a precise confidence interval estimates. Okay, one new thing we will talk about tonight are confidence intervals when the population standard deviation is unknown. I don't know if you remember that from last time. The population standard deviation was given to you, but it won't be given to you in the real world, so we'll just learn what to do in that case. Okay, so we talked about statistical inference. That's just a fancy way of saying you'll take a sample and you will infer something about the rest of the population. So out of your sample of 100 teenagers, you will infer something about millions of teenagers. When we sample, we want our sampling process to be completely random. And we call that simple random sampling. Now, it will make sense to you that if you want to find the average income in a certain town, you don't just ask all of your friends at the club, because they're going to have a certain level of income because they're at the club, whatever that club is. At the same time, we talked last week about how we want this sampling process to be completely random. If it is completely random, then we can use what we know about the normal distribution, because things fall into a normally distributed pattern if they are completely random, if we have large numbers, and if there's nothing skewing the distribution. So we need that randomness when we sample in order to rely on that normal distribution. We talked about this coin flip example. We said, suppose you flip a coin 20 times and count the number of times that it comes up heads. And we actually did this calculation back in class 1. We know the probability of each and every one of these outcomes. The probability of 5 coin flips coming up heads, the probability of 11, of 12, whatever, so on and so forth. We know all of these probabilities. And we said, well, let's assume we know this, but let's look at another group of researchers who do not know this information, and let's think about what they would do if they had to sample to try to figure out what this population mean was in reality. So, the thought process went like this. All right, we're statistics students and we know statistics. And we're watching maybe through a glass door or something, another group of researchers, just observing what they do. They assign all 10,000 Mercy College students to go home, flip a coin 20 times, write down the number of times it comes up heads. This group of researchers, they want to know what is the average number of times it came up heads. In other words, what is the true population mean? Alright, so true population mean, they want to know what it is. So they take a sample. They can't talk to all 10,000 students. They can only talk to a sample for whatever reason. And they calculate a sample mean based on a sample size of 30. So they ask 30 students, simple random sample selected randomly. How many times did your coin flip come up heads when you did that experiment last night? They add them all up, they find the average, and let's just say it comes out to 10.2. So they see the sample mean came out to 10.2, and they're wondering, how close is that to the true population mean? If we asked all 10,000 students and they told us the truth, how close is that sample to what the actual accurate answer is? Now, remember we're watching them through our glass door or whatever, and we know what the true population mean is. Let's just say that the population of Mercy College students who did this example, it looked exactly like this. So what is the true population mean?
10.
All right, it's 10. We know it's 10. So I'll put 10 here. All right, 10. We know that. They don't know that. Then we asked a couple of questions. We said, how likely is it that this group of researchers could get a sample mean that is a pretty good approximation of the true population mean? And I brought up 2 points just to think through initially. We said, what's the probability of any one of these 30 students flipping a coin and it coming up heads 9, 10, or 11 times? Yeah, about 50. Okay, so how are you getting that, Tim?
16% for 9, 16% for 11, and 18% for 10.
Right, so it's just adding up these frequencies. All right, that's the probability of 9, 10, or 11. So any one of these 30 students has about a 50% chance of being very close to the true population mean. So now we might start to think, yeah, I think even though they only asked 30 students out of 10,000, I think they got a pretty good chance of getting a good estimate. Because half the students in their sample are going to say 9, 10, or 11. So that's half the data right there. The next question we asked is, what is the chance of their sample mean being wildly off? Being off by like 5. What's the probability of them having a sample mean that comes out to 15? And do you remember what we concluded about that? What's the likelihood of that happening?
Less than 1.
Very small. Tiny chance. All right, what's the probability of just one student in the sample flipping a coin and it coming up heads 15 or more times?
About 1.7.
Yeah, about 1.7, 2%. All right, that's just one student. What's the chance of all 30 students flipping a coin and it coming up heads 15 or more times?
1.7 to the 30th power.
What's that? Yeah, 1.2 to the 30th power, which comes out to a bit 1 in a billion, gazillion, trillion, something like that. So, just a rough estimate there. So the chances of the sample mean falling in this upper tail, tiny, slim, not happening. And the logic goes the same way as we work inwards. So 15 or more is 1 in a gazillion billion. 14 is 1 in a gazillion. 13, 1 in a billion. 12, 1 in a million. And then we get to 11, we're like, okay, maybe it could possibly be in this range. Or could conceivably be in this range. So now we know two things, which gives us reason to think that these researchers who got a sample mean based on just 30 students have a pretty good estimate. Because half the students in their sample are going to give them an answer which is pretty close to the true population mean, and the chances of them being wildly off, very, very slim. And then we said, well, let's look specifically and see if we can attach some exact numbers to how confident we are that they've got a good estimate. And our thought process went like this. Let's build something and call it the sampling distribution of the sample mean. Let's assume that these researchers, in theory, were to take a sample of 30 students, find a sample mean, and then do it over again. And do it over and over and over again 50,000 times. And they were to put all those sample means on a frequency distribution. And we're going to call that sampling distribution of the sample mean. It's a sampling distribution, like frequency distribution. A frequency distribution of what? Sample means. So we'll put frequency here. We'll put outcome here. Alright, so if the outcome is 10, we'll put it here. We may see some 11s, some 12s, possibly 13s, 9s, 8s, 7. Alright, so the first sample mean they get is 10.2. Suppose they do it again and they get 10.4. Suppose they do it again, they get 9.8. Do it again, they get 9.74. Alright, so we'll keep going like that. Every time we get the same number as in a previous try, we'll stack these numbers on top of each other. Alright, and then we're going to end up with 50,000 points of data. It's going to be a frequency distribution. Let me ask you some questions about what this frequency distribution is going to look like. What is going to be the mean of this frequency distribution?
Approximately 10.
10. Approximately 10?
10.
10. 10. Alright, so the mean of the sampling distribution of the sample mean, so mean in this little footnote or subscript x bar, mean of sampling distribution of sample mean equals the true population mean. Why wouldn't it? Why wouldn't the average outcome be the right answer? It would. As long as they're using good sampling techniques, then their most likely outcome, the median outcome, the mean outcome is going to be the correct answer. Sometimes it's going to be a little higher, sometimes it's going to be a little lower. Now there's equal probability that it's a little bit higher and a little bit lower. So this is the mean equals the true population mean. Okay. We know the mean is going to be 10. Is this frequency distribution going to be normally distributed? It's going to look like a classic bell curve. Why do we know that? Because we know that we're using good sampling techniques. Nothing is skewing our data. We also know we have a law of large numbers. We also know that our sampling is based on complete random selection. Complete randomness. And this is going to be one of the many things in nature that fall into this normally distributed pattern. Normal distribution is something scientists discovered. They found it happened over and over again. Law of large numbers, nothing skewing the data, complete randomness. and we see this normal distribution. Now, it's possible there could be something skewing the data. Maybe, for example, these researchers are asking questions in a way that make the Mercy College students want to say they got more heads than they actually did. Maybe there's some stigma attached to getting to flipping a coin and getting a low number of heads, in which case that might skew the data. So we're assuming nothing like that is happening, and we get a perfect normal distribution. Okay. Next question I wanted to ask about this. What is the standard deviation of this sampling distribution of the sample mean? And let me ask you, is it greater, the same, or less than the underlying population? And this is the underlying population.
It should be the same. I believe.
All right, one vote for the same. Anyone else?
Less. Same.
Less. One vote for the less. We're even.
Yes.
2 votes for less? Okay. Yes. All right, less is the correct answer. The standard deviation is going to be smaller. And the reason is, this is the underlying population. The chances of these tails, any one student being in one of these tails, fine, it can happen. Maybe there's a 2% chance a student flips a coin and it comes up heads 15 or more times. But the chances of all 30 in any one sample, averaging out to 15 or more heads, not happening. 1 in a billion gazillion. So the sampling distribution, this is going to be very, very tiny until we get to the center, and then it's going to kind of look like that. But maybe a bit of an exaggeration. But the sampling distribution of the sample mean is going to have a tighter distribution because the chance of these outliers are much, much smaller. Specifically, a standard deviation of the sampling distribution of the sample mean is the standard deviation of the population divided by the square root of the sample size. Okay. Okay, so this is just actually what I just drew on the board. If we have a population distribution that is beautifully normally distributed, such as this, we take random samples and create a sampling distribution of the sample mean. It will be a curve that is normally distributed. It will have a mean the same as the population distribution, and it will have a standard deviation that is smaller than that of the parent population. So to review that, let's just read these terms again. Can someone read this top line to me?
The sample mean?
This right here?
Yeah, that's right. So you're saying you,
All right, what is this mu? What does that mean? Mean
so
of what?
the sample?
Mean
Oh,
of the
that's the
sampling
entire
distribution of the sample mean.
So this is the mean of the sampling distribution of the sample mean
Oh, the sample.
equals
So the population mean.
the population mean. Yes. So the mean of the sampling distribution of the sample mean equals the population mean.
Can we still say standard error?
Yes, you can. You could. Well, wait, we're not standard error yet. The standard error is not here. Standard error is down here. All right. So, what's her name again?
Kelsey.
Kelsey. All right. So someone besides Kelsey, because she knows the shortcut for this one. Can someone read this to me?
The standard deviation of the sample mean
No,
distribution.
sampling distribution.
Very close. Very close.
Sampling distribution of the sample mean.
Yes. Equals what?
The standard deviation of the population, square root over the sample size.
Divided by the square root of the sample size. Perfect. Now, we can call this the standard deviation of the sampling distribution of the sample mean. Could also be called the standard error. Perfectly acceptable. Okay, now what, I just gave you an example of an underlying population that is perfectly normally distributed. Sampling distribution of the sample mean works beautifully. What if I have a population that is not normally distributed? It may be hard to see on this, but this is skewed positively. It is right skewed. If this were income in a certain town, we'd have a bunch of rich people or maybe one rich person pulling the distribution up. For this population, we want to find the mean, the average income in this town. Can we still use the sampling distribution of the sample mean stuff? Yes, I have one vote for yes. Anyone else? What's that?
All the options we have.
You say no.
I mean, we say yes, because we don't have anything else to play with.
Yes, the answer is yes. It doesn't matter what the underlying population looks like. Sampling distribution of the sample mean stuff will still work. This population still has a mean. It still has an average. Now it might be a little bit higher than in the previous graph we looked at, but when we sample for it, we can still find it. The most likely outcome, the mode, is still going to be the mean. We're going to average out to the mean. Half the times we're going to get a little bit higher, half the times we're going to get a little bit lower, as long as we're using good sampling techniques, good sampling procedures. All right, how about the income in this town? This graph illustrates the income distribution. Kind of a weird town. Well, we've got a bunch of people who are unemployed, and then we have, a large number of people who are making very little income. And as income gets higher, the percentage of people making that amount gets lower and lower and lower, and there's just a tiny number of rich people. All right, so this is the town. I want to find the average income in this town. Let's just say it's right about here. Like maybe that's the average. If we add everybody's income up, including all the zeros and the people on the upper end, that's what it is. Can I use the sampling distribution of the sample mean stuff to find the average income in this town?
No.
I would say no.
Say.
We're just getting the average, a sample of the average, so every average will have the sample mean, which will always gonna work out to be around there somewhere, so.
Yes,
And we're
yes.
plotting that, and it's gonna stack up.
Yes, we can still use the sampling distribution of the sample mean. It will tell us the average. Every town has an average income, and that's all we're looking for. Now sometimes we're going to get a bunch of people who are unemployed, and we have one rich person that kind of averages that out. But as long as we have a good sample size, we're using good sampling procedures, this is going to work, and it's going to tell us the average income. Now, once we get that average, and we have this sampling distribution of the sample mean data, we do lose sight of what the underlying population looked like. So we don't know that this town had a weird distribution once we look at the sample outcome. Does that make sense? We lose sight of what the underlying population looked like, or we never knew what the underlying population looked like. That was the extra credit question, which was difficult on the quiz today. There were questions that tried to ask you questions. There were questions that tried to assert you could say something about the underlying population, and you could not. Once you get the sample mean, all you know is the likelihood that the sample mean will be within certain parameters. You don't know really anything besides that about the underlying population. Okay, let's review these terms one more time. Someone read this to me.
Mean
Go.
of the sample distribution of the sample mean
Yes.
equals mean.
The population.
Population mean.
Or sample distribution of the sample mean.
The mean of the sampling distribution of the sample mean equals the population distribution. All right, and then read this one. Somebody else? Chris, you got it, right?
Standard deviation of the sample and distribution of the sample mean
Equals?
equals the population standard deviation over square root of sample size.
Yes, okay. And the reason why I make you do this again is because this is the slide where we learned there was a shortcut for this standard deviation of the sampling distribution of the sample mean. We can call it standard error. Statisticians call this concept the central limit theorem. As the sample size gets larger, the sampling distribution of the sample mean rapidly becomes a normal distribution, a perfect bell curve. And what we mean by larger or large enough is a sample size of 30. As long as we have a sample size of 30, we can use sampling distribution of the sample mean stuff, regardless of the shape of the parent population. Now, one thing which will become somewhat of a factor tonight is the second bullet point. Whenever the population that we're drawing from, the parent population, is normally distributed, we don't even need a sample size of 30. That makes sense? So suppose we're drawing from this perfectly normally distributed population of incomes. We wouldn't even need a sample size of 30 to assume that the sampling distribution of the sample mean is normally distributed. We could have a sample size of 5 or 4. And we could still use all those sampling distribution of the sample mean concepts. All right, so this is how we constructed our confidence interval. We said, what is the sample mean we got? And let's plus or minus some number of standard errors. This standard deviation of the population divided by the square root of the sample size is our standard error formula. And we need to plus or minus some number of those. What number of those? Well, it depends on how confident we want to be. If we want to be 68.3% confident, we plus or minus one of these. If we want to be 95.5% confident, we plus or minus 2 of these. If we want to be 99.7% confident, anyone remember this one? 3, yes, 3, okay. We can choose those, or we can choose any number in between. We can be 80% confident, 60% confident, 95, 96, 99 is a common one. 95% confident and 99% confident are both common numbers, both common confidence levels. Let's do a quick example of that now. Suppose we want to be 80% confident, all right? How many standard errors, plus or minus, are we going to need to we're going to take our sample mean plus or minus a certain number of standard errors. How many of those standard errors will we need to use? 80% confidence. So, I think the best way, each time you have a confidence interval, is to draw a picture and think it through. So if I'm going to be confident that I'm 80% confident, in other words, I'm going to get it right 80% of the time. What percentage of the time am I going to get it wrong? 20. Okay, and tell me about that 20%. Am I going to be high 20% of the time, low 20% of the time?
10 and 10, right?
Half and half,
10
all
on
right?
one side and
10% of the time, I'm going to get a sample mean that is too high. 10% of the time, I'm going to get a sample mean that is too low.
Oh, yeah, I'm not gonna.
So I need this z value, alright? The one that separates the upper 10% from the bottom 90%. I also need this negative z value that separates the bottom 10% from the upper 90%. Lucky for us, we only have to find one of them because we know that it's just a symmetrical plus or minus on the other side. So, the great thing about the z-table is it tells us the cumulative area below a z-value of that particular magnitude. So what we can do is we can look in the center of the z-table for 0.90, and that will tell us the z-value of which 90% of the data is less than.
1.29.
Alright, so everyone see that in the middle of their z-table? You look for 0.90, and you may have to choose between 0.90 and 0.889 or 8.8995.
So you always go to the higher, right? Not the lower. You don't go to the 8, you go to the 9.
If you're on the positive side, I like going to the higher z-value.
The higher one,
It's higher.
oh, the,
But if you're on the negative side, you wanna go to the lower end,
8621.
so that's why it would have been 1.28 with,
Yeah, yeah.
Oh,
That's not what you did, right?
yeah, I went to the positive z table and I did 1.29.
No. I think you're thinking of something else.
No.
Yes.
So when you're at 95% confident, you usually take like the very ending part of the normal distributor thing and divide it by 2, the 5 I'm talking about.
Yeah,
Then we get 97.50, right?
yeah,
And then are we doing the same thing for this guy?
yeah.
So okay, the answer, I got another answer.
What do you get, Thomas?
1.04?
For 80% confidence?
Right,
What do you get?
which is 85.08, the percentage.
No,
So if you're-
that's, we're doing
104.
90%.
We're doing 80%, this is 80%.
80%, but you have to
Right.
split the 20, and then you do greater than 10, which is 90, right?
That's
So you're
correct.
looking for 90,
Right.
Are we looking for
0.9015.
90?
Yeah,
So 80%, but you have to measure it.
so we're 80% confident. Okay, so we're gonna be right 80% of the time. Of that 20% of the time we get it wrong, 10% is gonna be too high, 10% is gonna be too low.
Right.
So when you look at the z-table, you look at the z value that separates the upper 10% from the bottom 90%. If you had a negative z-table, you would look at the z-value that separates the bottom 90% from the upper, the bottom 10% from the upper 90%. And the answer would be plus or minus 1.29.
No, that one is actually 1.28.
Cause that's the quiz is 1.28.
Yeah, but you want to use the same. Just use the same. And I like to use the z value that has the highest absolute value. So if you're on the positive side, take the bigger one. If you're on the negative side, take the smaller one. If you chose 1.28, it would not be wrong. It would be certainly reasonable. Okay, but everyone's good for at least deciding 1.28 and 1.29.
Yeah.
Everyone's good there? Alright, so I think I wanted to do some practice problems here. Let's do page, take a question?
So on the quiz or the exam, you're gonna, if we choose either 1.28 or 1.29, you're gonna see it that way?
Yeah, that's fine. Yeah, sorry. So let's do page 249, number 23. And again, I think the best way to learn these, explain them to your partner, talk it through, practice reading the z-table together. Take a couple minutes and we'll regroup. Feeling good, Nick?
Feeling good.
How do you know if it's gonna be this one or this one?
No, because you have to get closest to 95. No, closest, this is great, it keeps going up. Right? You don't want to keep moving to the closest to 95. Right.
The thing, and that is 1.65.
What's your name again? Got it, sorry. Hey, what's your name again?
Ariel.
Ariel. Okay, good. How's this feeling?
So now
Ariel?
it's, yeah.
Yeah, we're.
So you're okay with it?
Yeah.
Ariana?
This one we do
What's your name?
90.1.
Ariel. Ariel.
Yes.
Got it, Ariel.
90.1.
Devin.
Yes.
That's the second one, 80. That's B. Yeah, we can get the answer. I'll just do them both at the same time. And we have them stay. C equals, 1.2. But that's the big one, right? So now we're going to put that in calculation.
Extended deviation.
So we just need to find the.
Is it a thousand?
And we're still gonna use the same.
Didn't work out as good, but I'm trying
Stats is Roxy.
Christy, feeling good?
deviation over square root of n.
Yeah, that much rounded, though. I think that's. Yeah. I would recommend keeping it in your calculator. No, 9.5. I don't know
No, I have an actual, I have one of the older, graphing calculators. I don't have that.
So I have to.
On the answer now.
So,
Monica, how you feeling? Should we do it together? Are we ready to start this? 2 minutes. Of course. It was a good look. It's coming back. Good. You're using your phone? Yeah. Yeah, I like that. Yeah, all these like instructions. Yeah, this is
It's just.
Yeah, I think this is good. This is like a finance calculator. Yeah. Good.
Cause you know what that got.
That's way to do it.
But you know with the pie,
That's the time of learning that. That's a right. All right, let's go ahead and do this problem. We'll see how far we get, see if we need to take a break between the next parts. In this example, you're trying to estimate the average age of moviegoers. So you want the mean age of every moviegoer in the United States. Millions of them, right? This could be important to you if you're a movie studio, you want to know what kind of movies to make. If you're an advertiser, you want those commercials before the movies, who are you advertising to? So you take a sample of 1,000 moviegoers. You find a sample mean of 39. You happen to know the population standard deviation of 9.5. This is going to help you because this 39 years old, that's just an estimate. You want a confidence interval, and you want to be 90% confident that that interval contains the true age of every true mean age of every moviegoer. All right. So ultimately, for the confidence interval, we're going to take 39 years plus or minus some amount, plus or minus some number of standard errors. Let's calculate our standard error to start. Standard deviation of the population divided by the square root of sample size.
It's 0.30041637.
Good. Outstanding. So I like to keep that, if you calculate that, I recommend you keep that in your calculator or keep that in Excel so you can apply it to the next step of the problem. If you round it right here, you could have problems depending on how many times you need to use that number. Alright, so standard error is that. How many standard errors plus or minus do we need to go to be 90% confident?
What did you say that?
1.65.
How many standard errors plus or minus do we need to go to be 90% confident?
1.65.
Very good. Everyone happy with that? Let's do it. So plus or minus 1.65 times 0.3004. This whole number kept in your calculator. Now, what does just this part, what does that come out to? Can someone tell me that?
All right, let me try.
I didn't use the 4, so I have to recalculate everything.
Calculate everything.
0.4957.
0.4957. Okay, so we're going to take 39 plus or minus 0.4957 is going to give us our confidence interval. Now we're going to learn a new term for this part tonight. We're going to call this part the margin of error. So I'll start throwing that out a little bit before we get to the slide. Our margin of error is 0.4957. So when we take 39 minus the margin of error, what do we get?
Okay, wait.
38.5043.
Okay. And what do we get when we take 39 plus the margin of error?
39.49.
All right.
I'm sorry, Professor, where did you get the 0.3004? I missed that.
Okay, so this is our standard error
When you divided 9.5
by the square root of 1,000.
Which is 10, right?
No.
It's 100.
I'm sorry.
Is that it's not a,
Square root 100 is 10. This is 1,000.
yeah, so it's like 33 something.
Okay.
Yeah, it's weird. It looks like it's going to be a
It's
simple
like 31.
solution, but it's not. Like, wait, that should have been easier. And you know why we get the standard error, right?
Well, then you got 39.497, that's what the age.
Yeah? Okay, yeah. Aline, do you want to do the interpretation for us? It starts with I'm 90% confident.
Well, I'm at 95% confident. of the third, of the standard deviation of the,
Alright, hold on a second. What are we trying to find in this problem?
the
Average
average.
age of
Anything else?
Average age of every moviegoer, and we sometimes call that just the true population mean. Make things simple on ourselves. We could say either. So we're trying to find the true population mean, and we have a confidence interval that we're 90% confident of. So the interpretation goes, I am 90% confident that the true population mean is between 38.504 and 39.497. Yes, Keisha?
So is that always the interpretation, when you ask for the interpretation, is it with the results included in the interpretation?
I'm not sure what you're asking me.
Because on the quiz, that was like the extra credit question. For the
Oh,
interpretation.
the definition of interpretation, is that what you're asking me?
Well, on the quiz, one of the answers, the correct answer was the definition of interpretation, and the other one was, the one I chose had the results in it.
Sure, okay.
So when you're asking for the interpretation, you're asking for the definition, or you're asking for?
There's no easy answer.
Oh.
Interpretation. Interpretation is just a word. It's not like a specific status term.
Right, so you wanna write that down.
So for the quiz.
For the quiz, remember I said a minute ago I showed you the slide that had the really weird looking population and had the perfectly symmetrical sampling distribution of the sample mean. So when you take the sampling distribution of the sample mean, you lose sight of what the underlying population looked like. The wrong answers on the quiz on that question tried to ask questions, tried to say that you could say things about what the population looked like. Okay, great, so that's 90% confidence. Suppose instead we want to be, yes, Carol.
I'm sorry, I know it's just a digit off, but I'm coming up with 39.496, if anything, not 7.
All right, so you two should work together and argue about whether it's 9 or 6, 7, 6 or 7.
The calculator comes out to 49.57, so if anything, I'm gonna round off the 5 to a 6, not to a 7. That's what.
49, so yours comes out to 49 point, wait, no, 0.4.
49.57.
Just your last round off.
The bottom one, the 39.496. That one.
No, this one, let's talk about this one.
That's fine.
Okay, so you got
Now go
0.495,
down. The next one, the upper.
Your upper
That
limit,
one.
yeah.
this one?
Go down.
You have four
Right
signs.
there.
39.497 she talked about, yeah.
The 9 needs to.
It should be a
96.
6. That should be a 6.
Okay, thank you, Carol.
No, I just want to make sure because when you're rounding.
That is correct, yes. I made a mistake there, so when you round, you look at this number to the right of this number, and so this goes up, because this is above 5. Good point. Right. So what if instead we want to be 80% confident and not 90% confident? How many standard errors plus or minus do we need to go in that case? 1.29. Yeah, remember we did this one earlier? 1.29. Okay. So is our standard error, is that going to change?
No.
No. So, but this is going to change.
The number.
Yep. So we're going to go 1.29. All right. And then remember I said our new term for tonight is this whole equation. And what does the, and this is our margin of error. What does this whole equation come out to?
1.59.
It says 3875 or 76 and you round it, right? No, it says 0.387516, but I know it's 75. Or 0.388. Do 3 numbers or 4 numbers?
0.388? Know what it comes out to?
Yeah, because it says 3875.
Okay. Is that right?
Yeah.
You all like that? Okay. Good.
0.3875, are you doing
Do
3
you want
numbers
the
or 4
75?
numbers?
That's what I'm asking you on 4 numbers. Cause it's
What?
3.3875.
So I would store this number in your calculator
Okay, keep that.
because you're going to add and subtract this from 39.
So leave it at 3875, guys.
Store it in your calculator, add and subtract it from 39, and once you get the final answer, then that's the case you have to round. I'd round to 4 digits.
So
3875.
this should be
So
three, eight,
if,
seven, five.
yeah, if you're gonna round it, then that's 4 digits, so that should be
3875.
3875, yeah.
Alright, so that's our margin of error.
Right, because it said 4.
So what's the lower bound for our confidence interval?
All right,
Oh, you want to go lower.
all right. So, 39 plus 1, 3, 8, 7, 5. When you get 39.38.
Anyone have the lower bound for me?
38.61.
And then 39.3875 for the high, for the price.
Okay, very good, okay. Adamus.
So to the very, very end, to get an answer, you must use all decimal points at all times, that's,
That would be my recommendation.
okay. I was just rounding off to the closest two, and I was getting basically the same answer, very slightly close, but not the
Yeah.
same, yeah.
And what's gonna happen is once we start doing percents, you'll realize that this second decimal point is a whole percentage. So if you round this off, you could be off by like 5%.
That one, 38.61 is wrong, because it says 38.6996. Yes,
Like 38.7?
yes,
Okay.
here it is, 39, take away .3004.
Alright, who can do the interpretation for us?
Right, but you have to do the 39 first. You gotta do the 39 plus and add.
Remember that, multiply those two and this number, and then you add that to it, and it's the
Gonna try it, when did, no?
it's the same.
Right, you're supposed to subtract the 3004, not the
I'll say it.
38575.
Yes,
You're
Joanne.
doing
I
it.
am 80% confident
I know this.
at the average age
No, we agree
or
with that.
that the average age of the average moviegoer or the average or the true population mean is between, at least I could use one or the other, between 38.70 and 39.38.
Very good, very good. I have issue with the way you said the first one. You said the average age of the average moviegoer, just the average age of every moviegoer.
Of every moviegoer. Or I can say the true population.
Yes, perfect. Okay, do you want to do this, do we do this one, where we change the sample size? Do that? Okay. So suppose instead of 1,000 sample size, we have a sample size of 2,000.
You're supposed to.
Okay, so now our standard error is going to change, and it's going to get smaller, which is good. We can give a more precise estimate. Alright, obviously this stuff is going to change. So, we take the square root of 2,000 in the denominator here.
And it's
Right, what do we get for our standard error?
the one that's,
What'd you get, Amanda? Standard error?
But I don't have the full number, so you want the full number.
Is that it? Is that it? Is that right? Do you like that, Chris?
I got .21 also, I don't remember the.
I got .224.
2124?
Yeah, like she had.
Okay. Alright, so we have a new standard error. So our confidence intervals are gonna still stay the same for 90%. Yeah, they're gonna stay the same.
Yeah.
90%, 1.65 times 0.2124. Okay. And what's that margin of error gonna be?
This is still the same.
That's for 90,
3504.
that's for 90, right?
Yes.
It's .35046.
35046.